Okay, let's look at a couple of examples of solving linear equations. Okay, example number 1. 2x plus 1 equals 3x minus 7. If we're seeking the value of x that makes this true, note that this would be a lot easier to solve if we only had one occurrence of x in the entire equation. To that end, notice we have a 2x here and a 3x here. If I subtract 2x from both sides, right, then 2x minus 2x, that drops off there. You're left with only a 1 on the left-hand side. On the right-hand side, you have a 3x minus a 2x. That's a single x minus 7. Okay? Now we have a nice clean equation. It's very, very easy to solve. One occurrence of our variable. The first and only thing that's happening to x is we're subtracting 7 from it. To undo that subtraction of 7, we simply add 7 to both sides. On the left, that makes 8. On the right, the addition of 7 and the negative 7 cancel out, and you have your solution. Okay, so x equals 8. All right. Now, 9 times out of 10, that's how these things are going to work out. You have some linear expression equal to some other linear expression. You're going to be able to find some x that makes that work. But there are a couple special circumstances we need to be aware of. Consider this one. A little more complicated. X minus 3 plus 2x minus 1 equals negative 1 plus 3x. Here again, our overall strategy is to get this down to a single occurrence of x just on one side of this equation, and then we could just undo the things that are happening to x in reverse order. Here we have an x plus a 2x. Those things could combine, right? We can collect like terms there to get a single 3x minus 3 minus 1. Here again, don't write them separately. Let's combine those. The negative 3 minus 1, that's minus 4. And then on the right-hand side, we have negative 1 plus 3x. So we were able to reduce, collapse these two occurrences of x down to a single occurrence of x on the left by collecting like terms. But we still have two x's here. We have a 3x here, we have a 3x here. So I'm going to take a cue from the previous problem and try to subtract off one of those things. If I try to kill off this 3x, for example, by subtracting 3x from both the left-hand side, and to play fair here, we have to subtract it off the right-hand side. Notice what happens. 3x minus 3x cancels off, but then so does this one. And you're left with negative 4 equals negative 1. That can't happen. Negative 4 is never equal to negative 1. There is no value of x that is going to make that statement true. Okay, so there is no value of x that solves this equation. We then say the set of all values of x that solves this is empty, and that's the symbol for the empty set. Or we could just write no solution, I suppose, too. Okay? Now, one more example. Suppose we have, let's say, 2x plus 1 plus 3x equals, let's say, 5 plus 5x minus 4. Okay? Here again, the strategy is to get this down to a single occurrence of x just on one side. We have some x's here we could collect together to get 5x plus 1 on the left, adding the 2x and 3x. Over here, we can't collect anything together with the 5x on the right, but we have a 5 minus 4 I can collect together. So that's going to be 1 plus 5x. And you probably see what's going to happen now. But just in case you didn't, suppose we try to kill off this 5x like we did up in this previous problem by subtracting 5x from both sides. Sure, it kills it off from the left, but just like example number 2, it also kills it off of the right. And we're left with 1 equals 1. Now, this is a little different than the example we had over here, where this was a statement that was never true, no matter what x was. Here we get a statement that is always true, no matter what x is. So I can literally plug in any value of x into this expression, and it's going to work. Okay? So your solution set in this case is the set of all real numbers. Any real value for x will satisfy that equation. Okay? And those are pretty much the three things that can happen if you're solving linear equations. You're either going to get a single solution here, you're going to get no solution, or possibly infinitely many solutions.